All right. Okay, good afternoon to all of you. Okay, we shall continue on another chapter, which is chapter 4 on the components of system units. Right, these topics will use about 3 hours. That means the whole week we'll be talking about components of system units. Right, there are quite a number of subtopics here. Right, hopefully for today's, we are going to talk about these few modules. Right, first we will be able to differentiate among the various styles of system units. When we talk about system unit, we know the easier one is the desktop PC, the box. But there are many other different types. Remember, we have up to 7 categories of computer. Right, so say for example, a notebook, you should be able to identify the system unit of the notebook. Is it different from the desktop? Okay. Right, the next we are going to identify the components within the system unit. There are different components inside. Right. Okay. Thank you. Right. We need to be able to know what are the components within the components of the so-called the motherboard. One important electronic is the motherboard, and we need to identify the component within the motherboard. The motherboard is part of the system unit. And we drill in further. At the motherboard level, we can see many different components, so-called the chips or IC, right? We need to be able to tell the processor and also how the computer complete a machine cycle. We'll talk about machine cycle. What is a machine cycle? And also be able to identify what are the various processors in use in your PC or notebook nowadays. Typically, we talk about the AMD and the Intel chips. And also, if we still have time, we'll talk about how to define a bit and also combining the number of bits to make a byte. And with the byte, we will be able to talk about encoding system. Right? We have a number of encoding systems, so we'll talk about that. Right, the next 2 hours, we'll continue on the memory system. What are the different types of memory? Right, and also we'll talk about the adapter card as well as the expansion slot. These are the things that we add on to the motherboard to enhance the function of the motherboard. Certain things that we need not to use now, we do not buy it. Only when we need to have that additional function, then we buy the additional adapter card. And also we talk about the ports and the connector. What are the difference between the two, right? Sometimes you believe that look like the same, but they are different, right? And also we talk about different types of buses and how they affect the system performance. Also finally we talk about power supply, okay? Also that should cover all the 3 hours. Okay, first thing first, what is the system unit? It is a case that contains the electronic components. We know that computers have many electronic components. And this case will house all the electronic components that we use to what? Process data, right? We know computer process data into what? Into information, right? So over here, this picture shows you all the different style of system units. The one that we normally see, the most common one, is the desktop PC, right? And for desktop PC, we know that even the storage, by right, it shouldn't be part of the system unit, but it's built within the system unit. For desktop and the, for the notebook and the laptop, typically you can see that the keyboard and the pointing device, remember sometimes they have a little touch at the center for you to move the mouse or the touchpad. All these are built onto the system unit, right? So you cannot differentiate these two supposed to be in-out devices also built on top of the system unit. And for the mobile devices, you can see that input and display are part of the system unit. You cannot separate them, right? They build the display, LCD display, as well as the keys right onto the system unit. And for game machine, right, typically it doesn't come together with the input and output. So you have to buy a TV or LCD display just to be the output. Also, you need to buy the so-called joystick to be the input, right? So this makes all the different kind of computers having different style of system units. Right, let's talk about the most common one. Everybody might have one at home, the desktop PC. And what are the components within this system unit? A typical one will have the what? Drive bay, right? You have a number of bays that house a drive. Typically, you need to have one bay for what? The hard disk, one for optical drive, your CD-ROM or your DVD-ROM, right? And beside that, there should be a big power supply, 400 watts or 600 watts, to give all the supply to all the components inside the box. And the next to it is a sound card. Okay, for the bigger system, having good sound quality, you might need to have an additional sound card. I know that for the smaller low-end machine, normally the sound card are built onto the motherboard. But if you want to have a better sound quality, you can buy a separate card to plug into the expansion slot. Right. The next is the video card. Same thing. Some has already built into the motherboard. However, if you want to have good game experience, typically you buy a very powerful video card. The card itself can be even more expensive than the motherboard sometimes. And this card might need to have extra cooling if it's very, very powerful using high power processor, right? So you can see this also can be additional plug into the expansion slot. The next is the important one, the most important, the CPU, right? Typically, Intel CPU, like the picture here is Core i7. I think it's still among the best in this current state, right? And of course, for all processor, you cannot work without memory, right? You have RAM, and this RAM stick will be able to plug into the RAM slot, right? Usually you have 4, and depending on how much you need, you might not occupy all the 4. So you have expandability in the future, right? So you can see that these are the basic components built into the system unit. Right, one additional, the most important within the system unit is the motherboard, okay? Why they call it motherboard is the most important one inside. The other boards, sometimes they call it daughter boards, okay? So the most important one, the main circuit board, is the motherboard. And this is the main circuit board in the system unit. And it will contain the adapter cards, right? All these are the adapter cards. And also they will have the chips. First is the processor chip here. You can see the little square here. And also there will be memory chips as well. Memory sticks that plug into the memory slot. And the whole thing the motherboard sometimes is called the what? System board. Okay, if you heard about system board. Okay, many of you, if you want to assemble your own game machine, most likely you have to choose a motherboard. But if you want to buy the off-the-shelf, like the HP or Dell machine, normally they will pre-assemble everything for you. They decide the spec for you and you just buy. But if you want to have a good machine, you have to study which motherboard give you the best performance, which one will have the most expandability, right? So you have to make a choice. And just now we talked about this adapter card. Remember we talked about video card, audio card, network card, game machine. You have a very, very powerful graphic cards, right? So all these are to provide the function that are not built into the motherboard at the time when you purchase the machine. Good thing about this adapter card is you can decide later, right? When you do not have enough money to put in so many good cards, so you can always wait. Initially, you may be quite happy with the graphic capability, and you just buy the lower end, right? So by the time you think that the graphic is too slow for your game experience, you might want to save enough money to buy a powerful graphic card or the video card to put into one of the slots here. So it does give you the expandability. The same thing cannot be said for the small machine like the notebook and the laptop, right? You got no additional space. Sometimes they might allow you to have one additional card, but very limited, okay? Not so much that. The most you can is put things external to the notebook, right? You cannot put inside the notebook itself. Right, we drew in one more level. Just now we talked about motherboard. Within the motherboard, we have seen the processor chip. We have talked about the memory chip, right? So now what is a chip? Not potato chip, right? So it is what? We are talking about processor chip and memory chip. Right, it says it's a small piece of semiconductor. When you talk about semiconductor, currently you have silicon or you have germanium. All these are considered semiconductor, right? And this material will allow you to etch electronic circuit onto it. Make it microscopic, very, very small circuit are etched onto the surface, right? And we call it integrated circuit, IC, right? With this IC, on the IC itself, you can, if you magnify high power enough, you will see all the electrical passage that allow you to carry the electrical signal, so that from a transistor, it can transmit signal to another transistor. And you are talking about millions of transistors or billions of transistors on the surface itself. And all these chips cannot be just simply exposed to air, right? They will encapsulate in a package. And two typical ones are here. One is called the DIP, dual inline packaging. This typically is for what? For small IC, like memory chip. Because for memory chip, you do not need to have so many signals. Typically, the pins will carry what? Address and data and some control, right? So the number of pins needed is quite small. So you can use a DIP, so-called, and pack it into like 20 pins or 20 over pins IC. For microprocessor, it's different thing. Like for this one, Core i7, can't imagine. It has what? 1,300 number of pins. And with that number of pins, if you want to make it into DIP, I think it will be like a big mini pizza. Yeah. Right, so you have to make it into a square and with all the pins on one side, okay? So this is called the pin grid arrays. 1,000 over pins, right? So with this packaging, with the pin carrying the signal outside, then you can allow these components to be attached to the printed circuit board. We call it PCB, right? Nowadays, the motherboard itself is a PCB, right? With a lot of electronic connection, together with the so-called pinhole that you can insert the IC and then solder it, so they will be interconnected. Right. Next, we move on to what is the main actor inside the motherboard, the processor. Is it what is the function of the processor? The processor, also known as what? CPU. You always heard about processor or CPU. They are used together, same thing, referring to the same chips. You interpret and what? Carry out the basic operation, the instruction, to operate the computer. Basically, you take your instruction and interpret and then execute the instruction so that data can be converted to information, right? And within this processor, actually, you can further break down into two smaller components. One is the control unit. The other one is so-called the ALU. Control unit, short form is CU, and the ALU is arithmetic logic unit. These two form a single core, okay? We like to say dual core, quad core, multi-core, right? So with this, basically, is a processor by itself. We call it a single core. And because of the competition, right, and also because the integrated circuit becomes denser and denser, you can pack more and more transistors into the same area, right? So initially, you're talking about million, now go into 100 millions or maybe 1,000 millions. That components can go onto the same chip. So they put more core onto the single surface, right? So we have such thing as dual core, quad core, and multi-core, right? So we ask the question, what are the dual core and the multi-core? A dual core, very simple. Dual means two, right? You have two CPU put into the single IC, right? Single packaging. And for multi-core, anything more than two, we call it a multi-core. Sometimes we can put in 4, put in 8, right? I think even the handphone nowadays with the ARM processor, you are talking about the lower end, right? Dual core. And then the mid-range is quad core. And then you go to the top end, at the moment, I think is 8 cores, right? 8 processors inside your handphone, right? So maybe I'll just show you typically Intel Core i7. It is basically a quad core. So from this IC itself, right, this is a dice, okay, the one that the semiconductor material that they etch the circuitry onto it, right. Of course, without this logical diagram, you will not be able to see what are they, right. But when they use a block diagram to show here, you can see that these are the 4 core. And they are identical. Basically, they just copy star dot star, right? If you make 1 core already, you just duplicate all the circuitry and you make it a quad core. From here, you can see that they have their own electronics. Together, there will also be a share area called the L3, level 3 cache. We are going to touch on this one in the next lecture. So this 4 core here will be sharing a L3 cache, okay? Cache basically is a fast memory, okay, to save the data and information temporarily, right? Right, as I mentioned just now, this i7 will pack into a packaging called a PGA, pin grid array. And all together on this side, you can see all the number of pins here, right? 1366 is 1000 over pins. Right, I think that's enough for the dual core and the multi-core. And he said every processor within this multi-core processor typically will run slower, right? They cannot allow it to run as fast as a single core. However, because you have multiple workers together, right? Each one runs slower, but when you have 4 or 8 of them working together, you achieve a higher performance. That's why when you have a so-called quad-core phone, smartphone, you think of the next level, 8, so-called 8 cores, right? So you hope that you can get faster response. Right, just a look at the internal of a dual-core processor. Remember, Intel came out with Core 2 Dual about 5 years ago, right? Inside, actually, they have 2 cores, CPU core, and also there will be a shared L2 cache. Everything built into the single IC here. This square here is having 2 CPU inside and some shared cache memory, right? And of course, when Intel did that, the AMD, the competitor, will also follow up with the same and sometimes overtake. Before Intel come out with quad-core, maybe AMD will come out one version first. They are actually fighting with each other, but I think at the moment AMD is losing out. Right? Most of the chips are supplied by Intel, but even Intel also face a challenge from the what? From the ARM microprocessor. Right? So look at here. This is the detailed microscopic view of the Core 2 Dual. And if you just take a close, just a far look, you do not see dual core. But I just draw a line at the middle here. Straight away, you can tell the 2 are actually mirror image. So basically, on top there's 1 core, below is another core, right? They are actually dual core, right? And this area is basically the cache, okay? It's shared by the 2, okay? The 2 core will be sharing a common cache memory. So we call it an Intel Core 2 Dual. Right, talk so much about the different number of core. Let's take a look at, for a single core itself, just now we mentioned that what make up the single core, we have 2 smaller subunits, right? We have a control CU, control unit, and we also have ALU, arithmetic logical unit, right? We look at each of these, what it does, right? Okay, it says the CPU actually interprets and carry out the basic instruction that operate the computer. Look at this diagram here. The processor is the main actor to coordinate all the activities. What sort of activities are there? First, for computer to work, you take input from the user, right? You as a user, so you normally make use of input device, like for example, keyboard or mouse, right? So your input device will input the data. The data will be copied into the memory, okay? And also the CPU, or so-called the processor, will actually communicate with the memory. What do the processor need to know? The instruction, what instruction to carry out, and what kind of data you are going to work on. At the end of that, they will produce the information. Remember, it processes data into information. So the information need to store back to the memory. So you can see that the information are bidirectional, right? Toward and back to the memory, okay? And the result information, you might want to see it on the output device, right? So we have output device here. So the CPU or the processor will have to send whatever information out to the output device. This is also another kind of activities. And not only that, for future use or for other people to use, you need to store the result back into the storage device. Storage device is like hard disk or the floppy disk or the optical drive, right? All these. So all these activities are carried out by what? The processor, right? The ALU itself go down to lower level. It will perform the actual operation. When CPU carry out, when the so-called control unit take the instruction in, it need to decode it and ask the ALU to perform the addition, subtraction, logical computation like AND or NOT operation, right? So these are the operations done by the ALU. Okay, so we go down one more level. Okay, we want to know detail internally. What does the CPU carry out? How do they carry out the instruction execution? Is it for every instruction, the processor will repeat a set of 4 basic operations. This set of 4 basic operations is also called the what? The machine cycle. This step 1, step 2, step 3, step 4. There are 4 basic steps that make up a machine cycle, right? So let's just go down to for every instruction, what the CPU will have to carry out, okay? The first one is to fetch. You look at here, the top one here, we have a mention here is a memory, below is a processor, right? So there will be a lot of activities between these two, between memory and the processor, right? The control unit will actually fetch the program instruction and the data from memory to what? To the processor, bring it in, right? After that, the control unit will have to decode. What kind of instruction, what operation to carry out? Okay, it has to decode. Is it addition or subtraction or multiplication, right? So you do the decoding, and also after that you generate the commands. The commands for who? The command is to pass on to control the ALU, the arithmetic logic unit, right? Because this is the actual actors to carry out the actual computation. So with the command and also the data passed on to the ALU will take over to do the actual computation. We call it what? We call it execute. This is a step for execution, right? So after the execution, the ALU is supposed to produce a result, or we call it the information. The result has to be stored back into the memory, right? So the control unit will take over. Step number 4 here. The operation is called the store. It will store the result back into the memory, and maybe you also want to show it to the monitor, LCD, right? Or you want to save it to hard disk for future use. So as you can see that for every instruction, basically it has to go through all these 4 fundamental steps. And remember, this is called the machine cycle. Maybe I'll show you a little bit more detail with this machine cycle. First, we know that the control unit, remember there are 2 small portions here, the control unit and the ALU, right? The control unit is the one coordinate and control all parts of the computer, right? And also the ALU will perform the actual ALU operation. Don't worry about this slide. I'll put up in the adventure for you to take a close look, right? So I'll just show you that the actual machine cycle, remember the 4 basic steps. So you look at here, this is the memory, this is the control unit, and that is the ALU, right? So the control unit will do the fetch the instruction and data from memory, right? Go into the control unit. The control unit will then do the decoding, right? It will decode and into commands. The command will use to pass on to the ALU. ALU know what operation to carry out together with the data passed on by the control unit. And you generate the output, right? Computation result. And finally, it will be stored back into the memory. And for every instruction, you go through this cycle forever, right? For each and every instruction. Okay, next, with that, we call it a single instruction cycle, right? So if you were to carry out this sequentially, it will be instruction 1, followed by instruction 2, followed by instruction 3. Every instruction will take, if each step here take 1 clock cycle. So for every instruction, it will take 4 clock cycle, right? Assuming you have a clock, right? So it will be too slow. So typically nowadays the computer do not work this sequentially, right? This is too slow for processor. So what they need to do is they improve the performance through what? This term here, pipelining. How do they do it? They will not wait for the first instruction to finish. As long as the first instruction go into the decode, the hardware will be free for loading the second instruction. That means instruction 2 will go into fetch. And as long as the first instruction go to execute, third step, right? The second instruction will go to decode. And there will be space for the third instruction to come into the fetch. And something like a factory belt, right? The production line, right? There are so many operators, each one will do a small job. At the end, there will be the final product, right? This is called pipelining. This diagram might not be so clear, that's why I come up with additional one to show you. Right, we have the timeline here, clock cycle 1, clock cycle 2, clock cycle 3, 4, and 5, right? So during the clock cycle 1, we will bring in the first instruction. The first step of the instruction is what? Fetch. We fetch the instruction 1. And when the time moves into the second cycle, right, the first instruction already moved into decode, right? And the second instruction will go into fetch. We will fetch in the second instruction. When you move on to third cycle, the first instruction go into the execute, and the second instruction go to decode, third instruction go to fetch. Right. For this example, I do not have the one similar to, we do not have 4 basic cycles. For this particular pipeline, we have 3 basic cycles. Right. So for these machines, we will have a machine cycle with 3 steps. Right. Then the first instruction is considered executed at the end of cycle 3. And then at the end of cycle 4, we will have another instruction completed, right? So as you can see that with pipelining, you always have 1 instruction completed per clock cycle. From clock cycle 3 onward, we will see that instruction 1 finished, clock cycle 4, another instruction finished, clock cycle 5, another instruction finished. So we will be able to achieve 1 instruction per clock cycle. Later I will make use of that. 1 instruction completed per clock cycle, right? So this is beauty of pipelining. Right, there is also another important components within the processor that is called the registers. And there are many of them, right? Typically in terms of 10 or 20 registers in a typical processor. What are these registers? They are the temporary high-speed storage. We know that their RAM also considered storage. We also have hard disk as a storage, but these are too slow for CPU. CPU need to have a high-speed storage in terms of what? Every clock cycle will be able to read or write. Okay, for each clock cycle, that means for a piece of data, when they read from the register, you talk about 1 clock cycle, right? For memory, it's not possible, right? It will take multiple cycles to get a piece of data in. And for hard disk, you do not talk into 1-2 cycles, it may be 50 or 100 cycles, right? So there are many different types of registers. We have data registers, we have instruction registers, instruction address register, and also others more than this, right? Let's take a look at these 4 basic types. The instruction register, what does it do? It says that it will store the instruction while it is being decoded. Remember, we will bring in the instruction from memory, right? The CU control unit will bring into the register to be decoded. That is called the instruction register. Over here, data register. Data register will store the data while ALU compute. Right, you have an ALU, you need to pass on the data to the ALU to compute. So you need to have data register as the input for the ALU. And how about the data register also used to store the result? Because after the ALU compute, at the end of computation, there should be what? There should be result. Need to be stored temporarily. So that is also using the data register. How about the instruction address register? It says that it stores the location from where the instruction was to be fetched. right? So in order to look for the instruction, the memory, you are talking about millions of locations. You need to pinpoint a particular location to look for the instruction or data, right? So this instruction address register will be the one giving you the address to look for the next instruction to be fetched. So the CU control unit will know where to look for this instruction, right? So these are just overall what are the register for, right? Remember, it is a fast storage, faster than the memory, faster than the hard disk, and only small amount inside the computer, right? For Intel architecture, in the past we are talking about less than 20. If you move, some of the EE students, if you learn the microprocessor, you will know that the number of registers is very small, only having a small quantity. Right, another concept here, we talk about system clock. Okay, this clock is not the real-time clock, or so-called the wall clock. Okay, so it says this system clock, in fact, is a crystal that produces a clock pulse, right? So control timing of all the computer operation. You need to have something to lock step. That means make every step synchronized. Okay, so you need to have this system clock to synchronize all the operations within the system unit. This will generate a regular electronic pulse. A single pulse is considered a clock cycle, right? A tick, a single tick, so-called. Just like a walk, digital clock, right? Every tick is 1 second, but here it's not 1 second. It's much, much smaller, right? So it says every tick is a clock cycle, and typically nowadays the computer you are talking about running with a gigahertz. Even your handphone is talking about gigahertz, right? 1.6, 2.2 gigahertz. 1 gigahertz, how fast is it? You have 1 billion ticks of system clock. That means that number of clock cycles within 1 second. Within 1 second, there are so many ticks within that 1 second, right? 1 billion, right? So when you talk about 3.8, means 3.8 billion. And this another term that we use to measure the processor performance is called the million of instruction per second. I think I mentioned in the earlier lecture. The term is called MIPS, M-I-P-S, million instruction per second. Sometimes people will say, what is the best performance of your desktop computer? Or after this upgrade, what sort of performance you can get? How many MIPS are there, right? So I use a simple example here. If your clock speed is equal to 1 gigahertz, okay, very common 1 gigahertz. So it is equivalent to what? 1024 megahertz. Mega is 1024,000, okay? Anyway, megahertz is quite common. So we have 1024 megahertz. And just now I mentioned that, right, the processor will be able to execute 1 instruction per clock tick. Every clock cycle, 1 instruction produced, right, completed. So with this analogy means if you have this 1 gigahertz clock, there will be 1024 million instructions executed per second. So equally to say that we can have 1024 MIPS, right? So with 1 gigahertz, if you can generate 1 instruction per clock per tick, okay, then the performance will be equivalent to 1024 MIPS. MIPS stands for million instruction per second. That is very fast, right? Within 1 second, it has already done 1 billion instructions, right? Okay, a little bit about what are the processors now in use for your desktop, for your notebook, and basically they are none from other from who? From Intel or from AMD, right? The two big companies that produce the processor for desktop computers, the PC, so-called. Even the Mac, right? The Mac is using the Intel processor. Besides mobile devices. Mobile devices are still dominated by ARM microprocessor, right? I think Intel is trying to break into the mobile devices using the Atom processor. Right, I think I don't want to go into detail about this table here. The first column are the names for all the processors. They normally have their own name to give the processor. And also they list out whether it's a single core or dual core or quad core, right? And also whether it is from Intel or AMD. they thus classify certain processor is for server class computers, and the middle portion here is mainly for desktop computers. The bottom here will be for notebook, so you can choose different one for different types of applications. Right, next we talk about heat sinks and heat pipes. You might have heard about heat sinks, but not so much about pipes. Okay, it said the processor chips will generate a lot of heat, especially you run at very high clock ticks. Right, in terms of 3.6 gigahertz, the processor will be very, very warm. Okay, some of you may run certain system utility that monitor the internal temperature. Right, you see that its temperature run up at 60, 70 degrees Celsius. Sometimes when you go very high, the system will shut down by itself. Okay, so it does generate a lot of heat that can cause a chip to fail or even burn. Nowadays they will not, okay, because they don't want you to reach up to that step and then burn the CPU. Internally there will be a temperature sensor. If the temperature go too high, then you shut down the system to salvage, make sure your CPU still survive. Right. In order to avoid that, normally we will have heat sink. And from this picture here, you can see there's a heat sink. Basically, they say components with fins. What is the purpose of having that metal piece with a lot of fins inside? I think if you study mechanical, you know that the heat dissipation rate increase when you have more surface area, right? The more surface area you have, the faster the heat dissipate, right? So that's why they make it into multiple fins, so to create additional surface, right? Surface area. And not only that, if the heat still trapped around the same area, then you will not be able to get rid of the temperature, right? So what they need to do is they will mount a fan to put on top of the, to suck away, to blow away the heat, so that the temperature will go down, right? And this is a heat sink. Next we look at what? The pipes, the heat pipes. He said that sometimes we might need to use liquid cooling. And the liquid to be used are typically water or oil, okay? And in this case, they will need to have what? The pipe. The pipe will be able to carry the liquid around, just like your car, you know. Your car will have to have the cooling system, right, to get rid of the heat. These are mainly for the server, right? And just now I mentioned about the pipe. The pipe might not are mainly for what? For the notebook. Notebook do not have space for a big heat sink. So what they need to do is they put in the copper pipes. Over here you can see if you open up the notebook, you have the copper pipe to carry the heat. And where does the heat go to? The copper pipe, you have to bring it to somewhere, right? They will bring it to a so-called exhaust fan. That fan will blow the hot air out. So if you have a notebook at one corner, one edge, you can see that sometimes the fan turns on, blow up all the hot air. And it's trying to blow away. The heat are all taken from the CPU, right? Another technique that they use to improve the performance, however, not so common, right? This is called parallel processing. How do they do the parallel processing? They will put in multiple processors. For this case, this diagram here, we have 4 processors. How does it carry out? Say, for example, you have an image processing. Image need to be processed. And the image is a square image. We can always divide the square image into 4 equal portions, right? And we will pass each quarter to one of the processor here. Because typically the image processing, you normally do the same operation, right? Assuming you need to do data compression or you need to do feature extraction, they will be applied to the same. They will apply the same operation for every part of the picture, right? So you pass one quarter to processor 1, 1 to 2, so on, right? And they will be carrying out the same operation, same instruction. However, you need to have a control processor, right, to schedule or to assign the job to each one of them. And then they will all process the same operation. At the end of it, because you chop the picture into 4 equal portions, you still need to combine it back to form the original picture as the output. So that's why we need to have a control processor that will recombine everything back into a single picture. So with this, in fact, you need to have an OS that supports so-called parallel processing. However, parallel processing is very common in the high-end machine, not so much on the PC, right? So we are not talking about PC having a parallel processing. PC has already have the core, right? Different 4 core or 8 core. Right, just now we said if time allowed, we'll move on to data representation. Let's talk about data representation, right? Okay, let's take a look at what is the analog signals and what are the digital signals. He said the analog signals are what? Continuous, okay? And I'll show you a diagram what do you mean by continuous. And he said vary in strength and quality because it's continuous. It will vary in strength and quality. The digital signal are in one of the two states, on or off, right? So I will just highlight with this diagram here, right? A digital signal can only have two, okay? Either on or off, right? So you only have two states, very clear cut. However, for analog signals, it's just like when I talk, the voice is an analog signal. It can be very low, can be very high, it's continuous, right? So this is called the analog signal. And what are the difference between the two? If you have an analog TV and a digital TV, then you can tell the difference when it's far away, right? For analog signal, when the distance is far away, especially in the older days when you stay in a kampong, right? And if the signal is weak, you see the gold images, you see the double images, you see a lot of white noise appear on the screen. However, you still can see the picture, right? It's very lousy quality, right? He said that if the signal is weak, the picture is weak, so you got no way to improve it. However, for digital signal is as long as the signal reach the receiver, right? You can see a clear picture. Either you get it or you don't get it at all. There's no such thing as blur image, okay? So for digital, you do get good picture if you can receive it, and then you get a whole. Either you get it or you don't get it. For analog, is you can get a substandard picture. So that makes some difference, right? There are pros and cons. Right. However, there's no choice. For computer, we talk about digital. We don't talk about analog computer. We talk about digital because most of the computer are digital machine, right? They work only with two states, on or off, okay? And because of this, in order to work, we will have a binary system. Because when you talk about on and off means 2, right? Base 2. And we have a binary system that uses 2 digits only, 0 and 1. And for a single digit, we call it a single bit. And you combine multiple bits, it will be a bytes, okay? I think the next slide will talk more about bits and bytes. And of course, there are some other number system here. We have talked about hexadecimal, means base 16. Or octal, we have base 8. Or decimal, we have the base 10. This is the one that we normally use for every day, right? He said we will need to, in order to implement all other systems, you need to have multi-value logics, and it's not reliable. For most of the digital electronics, we only have binary system up to now, right? We seldom implement multi-level logics. Okay, in order to have this, we need to have multi-level. Right, take a look at what is a byte, okay? So, by combining a number of bits, we will get a byte, right? 8 bits of 0 and 1s grouped together will form a single unit, that is called a byte. And for binary system, or in fact all number system, we will always make use of a positional notation. You need to know what is the positional notations. It said the position determines the weight of the number. We know all for the decimal number, the first digit is called a unit, right? It's times 10 to the power of 0. The second digit, 10 power of 1. Third digit is 10 power to the 2, right? So that is 100. First one will times 1, second one times 10, third one times 100, right? For binary the same, the first one will be times 1, second one times 2, third one times 4, right? So in fact we can have, if you want to convert a binary number into a decimal number, what you need to do is having a conversion template here, right? We know that 2 to the power of 0 is 1, 2 to the power of 1 is 2, and we have this template here. If I want to know this sequence of binary number here, what sort of decimal value, you just have to take the 1 with a 1. As long as you have a 0, you do not add the number. So I have a 1, I have a 8, I have a 32, I have a 64. You sum them up, you get 105. So with this 011, 01, 001, that is equivalent to decimal 105. Okay? So be able to do the conversion from decimal to binary or from binary to decimal, right? Right, what is a byte? Just now we said 8 bits together will group together to form a unit, and that is a byte. And you provide enough combination. With 8 bit, how many combination can you have? You can have up to 256 different combinations. So with 256, we should be able to represent all the different characters to form a coding system. So we can have a number represented. We can have uppercase or lowercase alphabets. And also we have all those special characters, right? Escape sequence, punctuation marks, even sometimes to ring a bell, right? All these will be represented by 256 different combinations. One example here is if we have 33 hex number here, it represents this pattern here will represent a 3. The other pattern here is a 5, and this one is a capital D, right? Okay, I think it's good time to stop here. So we shall continue on Thursday. Sorry, Wednesday, not Thursday.